So we have been working on conditional probabilities, and in particular, like we had this notion of how much whether information about the event influences the probability of some other event. Okay, and then we said like they actually give information about each other, right? So uh, we at the end of last class, I'd given you like a small example to work out. Um, Here, the universe was two die throws as normal, right? But now the probabilities were as follows. We said probability of 1 1 was 1 6, 1 2 was 112. No, actually 1 6. Okay, now when I write probability of 1 1, like what I actually mean is probability of the single element set uh, 1 1, but it's very laborious to write all of this, so I'm just writing a little abuse of notation. Okay, so here asked you to find a couple of things. Okay, right? What is the probability is through equals 1? Okay, so remember, this is our universe. The way we think about it, this is the outcome of A's die, and this is the outcome of B's die. Okay, so what's the probability that A's die shows up as 1? Okay, so tell me this event, the event that A's throw is 1, right? But tell me the event first. Let's do step by step. Right, very good. The event is 1 1 1 2 and 1 3. Every point on the universe where this statement holds true. Okay, and we saw how to assign probability to this set. This is the, we write it as a disjoint union. Okay, and because we know the probability of the single element subsets, this is 1 6 plus 1 6 plus 1 6, which is 1. Okay, so what is the, very good. Okay, so what's the probability is throw is 2. Right, you do it in exactly the same way, right? And I'm just going to write the final answer. It's 112 plus 112 plus 112 plus 1. Okay, what's the probability is throw is 3. Very good. It's the same story. Index. Okay. What's the probability this throw equals 1? Somebody else?
1 6 plus 112 plus 112.
Right. So this is the event 1 1 2 1 3 1. This is 1 6. It is 1/3. Very good. Okay. What is the probability this throw is 2? Very good. Same story. What's the probability this throw is 3?
Same 1/3.
Very good. So everyone sees how to do these calculations. Okay. Now what is the probability that A's throw is 1 given B's throw is 2? Okay. How do we do this? How do we calculate this? Okay. Let's do step by step. So the first step, very good. The first step is we write it as probability A's throw is 1 and B's throw is 2 divided by the probability that B's throw is 2. Here, the story is that somebody gives us partial information. Okay, they don't tell us the outcome, but they give us this partial information that B's throw has turned out to be 2. Okay, now we want to know in addition that is what's the probability that A's throw is 1. Okay, on top of the information that's already given to us, right? So if you combine these two, A's throw is 1 and B's throw is 2, what is the event? It's just a single element subset 1 2. Okay, so this corresponds to the event A's throw is 1 and B's throw is 2. No other outcome satisfies this statement with a true. Okay, and the denominators, the probability B's throw is true, which is okay. What's the probability in the numerator? The probability of 1 2 was 1/6. Okay, and the denominator was 1/3, and so this is 1/2. Okay, so here it was, when you look at it, okay, so the probability A's throw equals 1, okay, when we were not given any information on B's throw. Okay, when we were just asked what's the probability A's throw equals 1, uh, we said it was 1/2. Okay, now if somebody gives us the additional information that B's throw was 2, okay, our conditional probability that A's throw is 1 is still 1/2. It did not change. Okay, the probability that we assigned to A's throw being 1 did not change even when we are given this partial information that B's throw was 2. Okay, so can someone tell me what is the probability A's throw equals 1 given B's throw equals 3? Okay, so tell me more detail. Right, so this will be the probability of the set 1 3 divided by the probability of the set this throws 1 3 2 3 3 3, and this will be 1/2 as well. Okay, very good. Okay, so what is the probability A's throw equals 1 given B's throw equals 2? Somebody else? Okay, let me just ask some of you. So that way I'll also get to know your names. So I know, okay, hearing from you. Okay, so I'm just going to go according to my screen. So Caitlin, can you help me do this? Okay, yeah. So very good. So there's already an answer by Justine. So thank you. So Caitlin, I'll ask you the next question. And this is also 1/2. Okay. So here, uh, here like the probability is throw equals 1 did not change. Okay, regardless of what B's throw was. Okay. Well, actually we did the same probability twice, but it doesn't matter. Okay, so regardless of what happened to B's throw, in fact, like if I ask you this will also be 1/2. Okay, so in this case I've set things up so that B's throw does not give you any information on A's dice. Okay, and the way we know that is we know that this event does not provide any information on this event is that the conditional probability remains the same as the unconditional probability. Okay, so we have something like probability A's throw equals 1 given B's throw equals 1 is the same as the probability that A's throw equals 1. Okay, so that means that initially, without knowing anything, we gave this probability that A dice would come as 1. We are given that probability to be 1/2. Okay, now even if we are told that B's outcome is 1, it did not change anything about what we thought the probability of A being 1 is. Okay, so this is what we mean when we say that these two events do not provide information about each other, and we call these independent. The event A's throw is 1, it says independent, or B is 1 are independent. No. Will they be disjoint? Can, in fact, they definitely mean that they're not disjoint. Okay. So if you have two sets that are disjoint, okay. So very nice. So there's a very interesting question from Caleb. Uh, so we want to contrast with disjoint sets. Okay, suppose you have sets like you have a set A whose probability is not 0, another set B whose probability is also not 0. Okay, and but A and B are disjoint, right? So disjoint means they don't have any elements in common, right? So disjoint means their intersection is empty. Okay, so what is the probability of A given B? When we say probability of A given B, right, we would say this is the probability of A intersection B divided by the probability of B. Okay, and we don't know the exact values of the probability of A and B except that they're they're non-zero. Okay, now what is the probability of A intersection B if A and B are disjoint? If A and B are disjoint, what is A intersection B? Right, so A intersection B is the empty set divided by the probability of B. Okay, so the probability of the empty set we say has to be 0. Okay, we saw that when we were assigning probabilities, there's no other option for us. Okay, divided by the probability of B, but we know that the probability of B is not 0. Okay, so this is safe. So this will be equal to 0. Okay, and here, this is definitely not equal to the probability of A because probability of A was also not 0. Okay, so if you have two events that are possible, if A and B are two possible events, meaning that they have probability that is not equal to 0, okay, you most certainly know that if they are disjoint, they're not independent. Okay, and intuitively, why is that so? If I give you, if A and B are disjoint, right, and I tell you B has happened, okay, that means that A has not happened, right? Because they are disjoint, if B has happened, A could not have happened. Okay, whatever the outcome is, it's inside B. Okay, so it is definitely not inside. Because A and B are disjoint, it's not inside A. Okay, so if I already tell you that the outcome is in B, okay, you know the outcome is not in A. Okay, so they cannot, uh, disjoint events that have non-zero probabilities cannot be independent. Okay, and I mean the reason is that if one happens, the other cannot happen, so it is giving you information. The fact that one happens means that the other cannot happen. Okay, that's still information. Okay, does that make sense? Okay, so independent sets are sets, uh, right, so it goes back to the definition of conditional probabilities, right? Like, so what is probability of A given B? It means like instead of, so let's suppose this is our universe. Okay, instead of specifying a point in the universe, okay, I'm giving you partial information about the outcome of the experiment. Okay, so the universe contains every possible outcome of the experiment we are going to do. Okay, but rather than telling you the outcome of the experiment, I'm only giving you partial information. Okay, what is the partial information here? I'm telling you that whatever, I'm not telling you the outcome. Okay, but I'm telling you the outcome is in this set B. Okay, now if you have a different set A that is disjoint from B, okay, because I already told you the outcome is somewhere here, you know for sure that it's not in A. Okay, since A and B are disjoint, so it's actually telling you something about whether the outcome is in A or not. It's telling you that the outcome is not in A. Okay, so if A and B are disjoint, they can't be independent. Okay, yeah. Okay, so is everyone clear on this? So independence means that the sets intersect in exactly the right way. Okay, so independence means two sets are independent or they provide no information about each other when they intersect in exactly the correct way. Okay, and how exactly should they intersect? It's something like this: the proportion of A in the entire universe, okay, must also be equal to the proportion of A at intersection B inside B. Okay, so it just comes from parsing what we are saying. We say A and B are independent if probability of A given B equals the probability of A. Okay, now let us write this. Okay, so this is by the definition. Okay, now let's try to interpret this in a little different way. Okay, what is the probability of A given B? This is the probability of the A intersection B divided by the probability of B. Okay, now if this has to be equal to B are independent, probability of A given B must be equal to the probability of A. Okay, and therefore we must have probability of A given B is probability of A intersection B divided by the probability of B. This must be probability of A. Okay, or if you just look at these two, here it means that the probability of A intersection B is the product of the probabilities of A and the probability of B. Okay, so what is actually happening here is that you're looking at two pictures. Okay, for to understand independence pictorially, you're looking at two pictures. You're looking at the proportion of A inside the big box in the universe. Okay, that is like a it so probabilities are not proportions, it's not the number of elements. Okay, but to the extent the diagram can convey, okay, the probability, the weight that you give to this set A inside the whole um, universe. Okay, so that's the probability of A. Okay, now the conditional probability A given B is the weight you give to this intersection inside B. Okay, and these two ratios have to be the same. Okay, so that means that you cannot numerically illustrate it in the picture. Okay, but what it means is that A and B intersect in exactly the right way. Okay, and what is exactly the right way? The probability of A intersection B must be equal to the product of the probabilities of A and B. Okay, that is when A and B will be independent. Okay, does this make sense?
Can you repeat that last part again?
Right, so in order for A and B to be independent, okay, A and B must intersect in exactly the correct way. Okay, and what is the correct way? The intersection of A and B must have probability that is equal to the product of the probabilities of A and B. Right, so this particular equation, okay, this is how they should intersect. Okay, when two sets A and B intersect in this manner, okay, in this manner, uh, the probability assigned to the intersection is exactly this. Okay, that's when they are independent. Okay, that is the case where B will not provide any information about A. Knowing that the outcome belongs to B does not tell you anything about whether the outcome is in A or not. Okay, and it so happens that independence is symmetric. If A is independent of B, like if probability of A, uh, so if probability of A given B is the probability of A, that is knowing that the outcome belongs to B does not tell you anything about A. The converse is also, the other statement, probability of B given A also will be equal to the probability of A. Okay, so this will be my homework. Okay, and it's not very difficult to show. Rather than showing, like, I'll just tell you how to do it. So the way it happens is that if probability of A given B is probability of A, then we have shown that probability of A intersection B equals the probability of A times probability of B. Okay, but if this is true, okay, then you just divide both sides by the probability of A. Okay, and what is this conditional probability?
A given B.
No. What is the partial information? It's the one in the denominator.
B given A.
Right, so this is the probability of B given A. Okay, so the important point here is that if probability of A given B is the probability of A, okay, it automatically will hold that the probability of B given A will be the probability of B. Okay, so if knowing that the outcome belongs to B does not tell you anything about whether the outcome is in A, okay, the reverse is also true. Knowing that the outcome belongs to A will not tell you anything about whether the outcome is in B. Okay, so here, like, it means that these events A and B intersect in exactly the correct way. Okay, and that is what the meaning of like no information is. Okay, and we, in fact, like you often take this to be the definition of that. Okay, so does that make sense? Okay, to some extent, like we are moving from an intuitive notion to a very formal notion. Okay, when I say information, or when I say the word information, right, that means something to you because it's a word in English. Okay, so you associate it with some meaning. Okay, now what we are doing is like we are taking this concept that you have intuitively. Okay, but here we have a very specific formal definition of what information is. Okay, information here means that uh, telling you that the outcome belongs to one event does not tell you anything at all, does not change the probabilities that you assign to the fact whether this outcome belongs to another event or not. Okay, this is a very formal definition of what information is. Okay, and this is what happens many times when we quantify something that is fuzzy in language to something mathematical. Okay, what we usually do at this point is we replace our fuzzy notion of information with this. Okay, that's kind of what we are doing here. Okay, so we are, so every time somebody tells us like there is no information about this, we are actually now reinterpreting that statement in this notion. Okay, now keep in mind that when here the way we have formalized it is completely it's completely oblivious to how you're going to uh, infer one from the other. Okay, when I told you that if our definition here of A and B being independent means that if I tell you the outcome is in B, okay, there's nothing you can, there's no information provided to you about whether the outcome is in A additionally or not. Okay, and here it's not a specific algorithm that you use. I'm not saying okay you have to get information in this particular manner or in that particular matter, or you do this calculation or you ask this person or something like that. Okay, this is like universal, like you can do what you want in order to infer information about A from B. Okay, you can do anything you want, you can use all the supercomputers you want, anything you want, you can take as much time as you want, none of it matters. Okay, if A and B are independent, you will not get any information about A from B. Okay, does that, so it's independent of like how you're getting information. Okay, it simply means that the probability of A given B equals the probability of A. Since these probabilities did not change, okay, you cannot infer anything about A from B. That's how we interpret this. Okay, okay, so right, so this is information about two events. Okay, we can generalize it to more than two events. Okay, but before we do that, like again, like I want to step back and just give you a chance to ask any questions if you have any, both about either conditional probabilities or uh, independence. Okay, so you'll get a lot of questions about these in future quizzes too. Okay, the current quiz only has like very simple problems, just asks you to compute some conditional probabilities and so on. Okay, but the questions become more and more complicated as we go along. Okay, the good news is that at the end it is just this. Okay, at the end, whether or not events provide any information about each other is captured by this little equation. That is all that's there at the end. Okay, so it is just using this in many different ways. Okay, okay, so let us look at so what we'll do now is like we have all these notions of probability, universe, events, and so on. Okay, now we will try to expand these notions into like broader setups that we will study. Okay, and along the way we'll learn a little bit about combinatorics. There are not many results, but there are certain results in combinatorics that are very useful for us, and you have actually seen them already in class. We went over them without proving anything. Okay, so uh, so here is like um, here is like an experiment. Okay, so we are looking at coin tosses. Okay, so and the experiment is that let's see, Axel, right? Uh, so Axel does. I'll start with a number. Let me use a number I can write easily. Okay, and we label the we label the two sides of the coin. Okay, we label the two sides of the coin to be 0 and 1. Okay, so 3 coin tosses one after another. Okay, so this is the experiment. What are all the outcomes that could come out of this? Okay, what would be our universe? Very good. Uh, very good. And the way Brandon has written the universe, I write it like this. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Write it like this. I'll continue here. 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, this is the universe that we have written. Okay, very good. So, right, so both Caleb and Brandon have written in exactly the same order. Okay, so everyone sees why we write it out in this order systematically. So give me why. So tell me why.
Is it because of all of the possible opportunities for A, or I guess all of the combinations of A coin
Okay.
toss?
Right. So there are many ways to see it. Like this, not a unique way. There are many, many different ways to see it, and we'll look at all of them. Okay. One way is to think of it as a tree. Okay. So your first coin toss could come up with, you could show up as either 0 or 1. Okay, now if the at this node, okay, so this is something like you're doing the experiment in stages, 3 coin tosses. Okay, it is one experiment, but you're doing it in stages. Okay, at the end of your first coin toss, you throw the coin again. Okay, when you throw the coin again, you could get a 0 or a 1 here as well. Okay, so or rather these edges are 0. So this is the outcome of your second coin toss. The green one is the outcome of your second coin toss. Okay, but you would have thrown the coin even if your outcome of the first coin toss was 1. Okay, and at the end of it you would have got a 0 or a 1 again. Okay, then you would do the third coin toss. So at the end of 2 coin tosses, there are 4 possible outcomes. Okay, at the end of 2 coin tosses, you could have got a 0, 0, like blue 0, green 0, 0 0, 0 1, 1 0, or 1 1. Okay, now at the end of at the end of the second coin toss, you do another coin toss. Okay, so now you each of these outcomes expands into two more outcomes. Okay, so in this way, in your third step, you add a third outcome. Okay, so when you combine three coin tosses, right, so you have 0 0 0 here, for example, corresponding to this leaf node. Every leaf node here of your tree here is a possible outcome of your three coin tosses. Okay, this particular node, for example, corresponds to 0 1 and the 1. Okay, everyone sees that? Okay, so here when you write this is 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, you can also think of this if you write numbers in binary. If you write numbers in binary, what are these numbers? This is 0 1 2 3 4 5 6 and 7. Okay, why do we get 7? This is 2 to the 3 minus 1. Okay, and this is 0. So after three coin tosses, you see the binary expansion of all numbers from 0 to 7, or 2 to the 3 minus 1. Okay, and so there are totally 2 to the 3 outcomes. Okay, 0 to n minus 1 is n numbers. Okay, because we include 0 as well. So 7 plus 1, 8 numbers. Okay, that is your universe. So your universe is these 8 numbers. Okay, another way to think about this is like if you want to visualize, okay, you visualize this cube. Now this is a cube in 3 dimensions. Right, so this is a cube in 3 dimensions. Each axis, you start with 0. This is the x-axis, y-axis, and z-axis. Okay, one axis for each coin toss. Right, so you look at the coordinates of all these vertices. Okay, when you look at the coordinates of all these vertices, okay, so the origin is 0 0 0. Okay, uh, this this vertex for example, its x coordinate is 1. Okay, y coordinate is 0, and z coordinate is 0. Okay, this one is 1 1 0. Okay, this guy is 0 1 0, and so on. Okay, so these are also like the vertices of a cube. Okay, now these are different ways to visualize, but the concept here is the sequential tree representation really tells you what is happening. Okay, at the end of your first coin toss, you had two outcomes. Each of these two coin toss fans out into two more outcomes. Okay, so at the end of two coin tosses, you have 2 times 2, that is 4 possible outcomes. At the end of 3 coin tosses, each of the outcomes at the end of 2 trials, the 4 possible outcomes, each of them fans out into 2 more. Okay, so that gives you totally 8 different outcomes. Okay, if you did instead of 3 coin tosses, if you did 4 coin tosses, how many outcomes? 16. Very good. So if you did n coin tosses, many outcomes? Right. So what is happening is the first coin toss gives you 2 outcomes. Second coin toss multiplies it by a factor of 2 because each outcome fans out into 2 more. Okay. Then at the third coin toss, each outcome after you had two coin tosses fans out into 2 more. Okay. And that gives you 2 additional ones and so on. The end of n trials, you have n2 multiplied by itself n times, so there are 2 to the n different coin tosses. I mean 2 to the different n 2 to the n different outcomes. Okay, so everyone completely okay with this? Okay, so let's change this a little bit. If you had n throws of a 4-sided die, okay, how many different outcomes? Very good, 4 to the n different outcomes. Okay, so in order to remind ourselves of this calculation, right? So here we often write these sequences, okay, in terms of what we call the Cartesian product of sets. Okay, now we have seen, like, you know how to multiply numbers, okay? So but if I ask you to multiply sets, okay, that is clearly something weird, okay, but we actually give it a meaning, right? So we say the set 0 1, this is not a regular product, this is called a Cartesian product. Okay, so this is a set which captures this thinking, okay, it captures this thinking and formalizes it. What it means here is that your first set here, right, 0 and 1, I write it as like a tree whose it has 2 limbs, okay, well, each one corresponds to one of the elements of this set. The second set is attached, second set is also a tree, okay, which is 0 and 1, but you attach it to every single outcome of the first set. Okay, so the Cartesian product is the result of combining these. So I concatenate every element of the first set with an element of the second set. Okay, so this is the set which looks like this. Let me write this. Right, so the Cartesian product is the set of it's the set I get by concatenating every element of the first set with every possible element of the second set. So all possible concatenations. Okay, so if I took, for example, the Cartesian product of 0 1 with 1 2 3 4, what do I get? What's the size of the Cartesian product? 8. Very good. So let's call this ABCD so I can write a little easier. Yes. Okay, so what's the Cartesian product? I need to look at every possible concatenation of elements from one set with the other set. So can somebody help me write the Cartesian product? Very good. 0A, 0B, 0C, 0D, 1A, 1B, 1C, 1D. Okay, and what is happening here is, like, I have 0 1, and in the next step I concatenate it with this. Okay, and the number of elements is 2 in the first step. Every outcome of the first step gets fanned out into 4 outcomes of the next set. Okay, and so totally 8 different elements. Okay, does that make sense? Okay. So when you're looking at all these experiments, right, and you're doing it in a bunch of steps, okay, and you have this, so the outcome of the first step is a set, outcome of the second step is a set, outcome of the third step is another set, okay, and here the crucial thing is, regardless of the, when we say something like this, it means that you're doing the experiment in 2 steps. First step could give you 0, 1. Second step could give you A, B, C, D. Okay. The crucial thing here is that regardless of the outcome in the first step, whether it is 0 or a 1, okay, your outcome in the second step can be any one of A, B, C, and D. Okay. That's when you can multiply sets like this, and your universe is simply all possible concatenations. Okay. If on the other hand, you could have experiments like this. You could have your first step be 0 and 1. If it is 0, your second step could only show up as B, C, and D. If it is 1, your second step could show up as A, B, C, and D. Okay. Now there's no simple way to write this as a Cartesian product. Okay. We are only thinking of cases like this, where regardless of the outcome in the prior steps, your nth step has the same outcomes. Okay, so that's the simple case, which is also very useful for us. Okay, right. So now these are like more and more details about the same thing, but essentially this is a universe and this is a setup that is extremely important for us. Okay, these we call them as Bernoulli trials, and when we actually do random variables, we will say a lot more about this. Okay, because this is like an abstraction for many important questions that we think about. Okay, no one truly wants to throw coins many times, but the reason we spend so much time about coin tosses is that it captures an abstraction that is very useful in many cases. Okay, so any questions about this? Right, so this universe, because we could write it as 3 coin tosses, the outcome of any step is either a 0 or a 1, regardless of what happens in other steps. We say that the universe is this, and we often shorten this. I mean, since we are writing like a product here, right, we usually shorten this to be 0, 1, q. Okay, by which we mean the set of all sequences of length 3, okay, whose elements of the sequences are either 0 or 1. Okay, this is a super important universe. Would be more complicated. So there is, I think I erased it, but I can change this. If you have a setup like this, right, what we call this, so this is a subset of the Cartesian set. So this one is, so the set that you come up with is 0b, 0c, 1a, 1b, 1c, 1d. Okay, now this is a subset of the Cartesian set. 0 is, this is the subset. Okay, so we actually have specific names for these subsets. They're called relations. Okay, in fact, like in general set theory, even functions we think of as special kinds of subsets of the Cartesian sets. Okay, so this by itself, the more complicated situation where at the end of 0 you can only have a, b, and c, but at the end of 1 you can have a, b, c, and d. That corresponds to this set, okay, which is in general a subset of the Cartesian product of 0, 1 and a, b, c, d. It's not the Cartesian product, but it's a subset of the Cartesian product. Okay, and these subsets, like we study subsets of the Cartesian products too, and we study them usually under the name of relations and so on. Okay, so you have these different kinds of relations. I don't know if you have heard of them. There are these reflexive, transitive, uh, commutative relations. You have equivalence relations and so on. So these are also things that we study. Just for our level, in a beginning probability setup, we are not so concerned about situations like this. Okay, but rest assured that people study these things too. It's just not so simply written as a Cartesian product. Okay, it's just a subset of the Cartesian product. Okay, uh, okay. So right, going back to this example, one reason to spend so much time is that this is like really important as an abstraction. If you have n coin tosses, the universe is 0 1 to the n, okay, or it's the Cartesian product of 0 1 with itself n times, or it is the set of all length n sequences, and there are 2 to the n of these sequences. Okay, right, so everyone okay with this? Okay, so we'll stop here. So on Monday we will continue talking about this universe. There are a lot of more interesting things about this universe, and we'll continue talking about this on Monday. Okay, so thank you very much, and I'll stop recording now, but you can ask me questions.